I take it as you don't want to speak until you are on the record. like big artists speak only when the camera is on. So the goal. So why I know everyone knows what what do we get from the course? Which specific knowledge? What is your understanding by today?
The other day we were talking about like categorizing. It's more about like understanding like through things and different things and how they work and stuff.
Okay. Okay. And okay, categorizing. But what is the connection between this course and the rest of chemistry or rest of technology? How are you going to synthesize anything? Okay, so we have no synthesis. Are you going to characterize anything? Potentially, theoretically. Yeah. There will be no wet labs if you go on the computer modeling, but we are getting concepts sufficient to understand how the materials and molecules are characterized. Okay? Now, what is the problem? Why you can't just form as an unexperienced user, just approach the instrument, push the button, and get the characterization?
Slightly complicated.
It's not so that complicated. If you do not have ambitions higher than like technician, then it's fine. There are user-friendly instruments. But if you want to go about and design new things, or if you want to survive in a competitive environment, it's better to get an understanding of how this calculation fluids work. And what is the problem with understanding background properties of molecules? Why should we start? Is it maybe we are wasting time and you can you have enough knowledge to predict look at chemical structure of the molecule and tell, I know it will be green color. Maybe. Why? What's the problem? Well, I'm not trying to inspire to do something new compared to what we did last time. Like, based on what we discussed, what is the challenge in understanding properties of molecules? Why it is challenge for human intuition? Why it involves math? Why it is generally complicated subject, deserving special.
Outcomes of different things. Like kind of understanding properties. If we see like the similar properties and other things, we can kind of make an assumption that maybe a similar that will have like a similar trait or.
What it's a great idea, and there is a branch of science based on statistics, the so-called cheminformatics, when you just make a database, many molecules, some properties, and then you find correlation, like linear, then you extrapolate and pick everything. But it will work only if they have similar structures. If there is something you never saw before, it may not work. So we are trying to go microscopically to get all bells and whistles and internal structure molecules and predict what come out, what their ability to react or how they respond to electromagnetic radiation for characterizing their properties. And here we are hitting a challenge, which is
You have to come up with math models to model that.
yes, and why math models for molecules are what is not true.
can't see them so well.
Yeah, yeah. And what is like molecules are composed of nucleus and electrons. What is more complicated?
Electrons.
Yes. Okay. Why electrons are complicated?
So we can't like.
They
know
do
where
not
they are.
they do not sit in one place. They are distributed. So we need special mathematical tools for distributed objects. This is truly a challenge that we may want to address. Okay. So if we will be successful today, which I'm not 100% sure, which if I will be successful today in time management, we will arrive at a couple of equations. I just want to give heads up what they are. And you may have seen some of them. If you are acquainted with all four of them, you can just stand up and if you don't, then you may get something new. So the first one is this generalization of oscillating trigonometric function into so-called complex numbers. If you did have calculus, then you may decide to take it later, if you consider it fun. This will be no use of this formula for practical issues, but it will be philosophically main cornerstone. Just wave behind all these guys from the beginning of the 20th century, the Royal War. This is also a question that goes a little above from what we did in this course. It is a favorite equation of Richard Feynman, who contributed to this.
Could you move your mic up?
I thought it would work without mic anyway.
Okay, I think that's better.
Okay. So this is a question how to predict future. And the last one is the main equation of the overall course that we will be formulated either by the end of today's meeting or by the beginning of the next meeting. And we will be solving this equation for the rest of the course. It's Schrödinger equation that many of you have already seen at different occasions. I will try to use records of the meetings so you can look backwards or forwards in previous years. And what did we? Oh, I was browsing YouTube and Wikipedia, so we had double speeds. Or so here's out from gun. Here are two channels. And intuitively, one would expect that outcome would be flashes from the and due to wave nature, they were expecting to have something in between. Okay, it doesn't like this. Huh?
Cannot play media.
I see. It's always a challenge with doing incorporating videos into the PowerPoint, but we will get through it, and by the end of the course, you will generate videos and embed them into PowerPoints without problems, better than myself. So it is about where we stop last time. So the stuff that is getting quantized in Bohr model, the angular momentum times distance, by good luck, has the same dimension as action. Right? This capital S. And this gives us intuitive ability to make a guess that Bohr models tell us that only such trajectories where this product of momentum times distance gets to integer number, only such orbitals are allowed, right? Because what you have heard in your freshman chemistry Born orbitals were this angular momentum. Are trying to challenge ourselves with questions like why this waves oscillate, what is oscillating, what is going on as soon as we move along this trajectory. And through this analysis of dimensions, we can establish analogy and assume that this electron moves along this orbital trajectory, it accumulates action. And action, you remember, is the stuff that everyone wants to minimize. Everyone of us, not conscious humans, but objects, ions. And it is formulated as kinetic energy. If kinetic energy is minimal and potential energy is maximum, it's 20%, for example, if I do not move, I fall down on the software. Principle of this action. So, the main hypothesis is that as soon as electron is moving along a trajectory, and later on you will see that it doesn't move along one trajectory, it's extremely holding in coexistence. If it is moving, it does accumulate action. And there is a hypothesis that this action will directly affect phase of the oscillations. Distance times momentum action. They are both divided by Planck constant, which has the same dimension. You will not memorize its value. It's like 6 to the power minus 10 minus 34 joules times seconds, something like that. Okay, so it was attempt to recall, and now something new. What is phase? I had a student working with me, given a great answer. I was given offered a question about quantum phase, that we will discuss, but asked it in a very brief sentence. Oh, phase, I remember, it can be like gas, liquid, solid. So, no, I'm not telling you about this this phase. Phase of oscillation. Like, you know, if you do sine of the same function, there is an argument. And if argument changes linearly, for example, it is distance divided by wavelength or time divided by period. So the argument of the periodic function changes linearly, it grows, and oscillating functions oscillate. So argument of the oscillator function can be called phase. As further phase develops, the more and more oscillations. Make sense? So, based on all this philosophical discussion, there are more orbits. Something was oscillating, and the higher the momentum, more oscillations form. This would fit perfectly into a hypothesis that action divided by Planck constant will be phase of this cassette. So the larger the truth, the more oscillations are happening. You rise or port, digest, then I will tell that it is a So the life would be too easy if electrons would just follow sign laws. The situation is a little bit more complicated. And before we go forward, I need to give you first 5 minutes of the complex calculus. Lift hands if you have a quick complex calculus. Complex doesn't mean that it is so complicated. It's complex, it is a term. So probably you wouldn't mind to give a quick refresher. And it will help. And right now we do not have much homeworks problems because there are so many counterintuitive bricks that we need to put together before we can do actual things. So it is more philosophical work. Later on, we will go through regular areas in all other courses like piece of material. What is the square root of -1?
I.
Oh, then you know complex amounts, right? So there are some numbers that are not real. And if you take square root of -1, if you solve quadratic equations, sometimes you get answers that don't belong to real. And there are generalizations of the numbers, right? There are several classes there. Nature of numbers, number of elements, integer numbers, and real numbers when you divide something, or if you divide part of that would do less than 1 but more than 0, right? And we don't care much, but professional mathematicians do. And there is a next layer. If we come to sets of problems when we need to solve quadratic equations where answers can be unreal. And generally, the complex number is the summation of real and unreal. Okay? It was a big surprise for you. No surprise. Good. I'm so good. You are well prepared. So, in some sense, the complex number is a two-dimensional vector. If you do want to represent this vector, so you can visualize like regular numbers. It's just a point on a line, right? You're bigger or smaller. But for complex numbers, one line is not sufficient. You need a plane. In one axis, you put a real part and another imaginary. So you can tell that one complex number is a vector going from origin to C each imaginary, where C equals x plus imaginary I plus 1. Right? So it is Cartesian representation of a complex number. But sometimes it is much more beneficial to use so-called, instead of Cartesian coordinate, to use so-called polar coordinates. Give me a sign if you didn't. So everyone is proficient in polar coordinates. So then you measure distance from origin to the, your point on complex plane, and then you compute the angle. Right? And then you are writing that your then the distance, the radius will be just and to get the angle, which by can process it as triangle with a right angle, and you can compute the projections by as sine or cosine of the angle, right? But if you need to inverse, you do inverse sine to inverse cosine. So then your complex number is the radius times the vector of length 1. Cosine phi plus I sine. Okay? So if you have vector where projections are sine and cosine, you know that sine squared plus cosine squared will be always 1. It's vector of length 1. So an abbreviation to summarize this equation in much shorter notation. There is a convention how to make a shorthand notation for this polar coordinate. Anyone wants to suggest or help me? How can they report this writing in a shorter way? Okay, did you ever heard the last name, common name Euler? Starts with E. Okay, if you heard the name Euler, can you suggest what should I write here?
E to the I5.
Excellent. So it is a convention to abbreviate this writing in this form. So if you write exponential into the power imaginary times angle, it means that it is cosine plus imaginary times sine. I'm super lazy and laid back, but I would try my best to offer a little homework to practice this equation, because it makes life easier. Wait, so this stuff is called Euler equation. You got it. Trade. So we are ready to go to further generalization of the Broglie waves and Bohr waves. So right now, let's just believe it, and later we can try to develop more arguments. But description of this complicated distributed electrons would get much more natural if you assume that along the path, along the trajectory, something is oscillating not just as one component, but there are two components oscillating simultaneously, real and imaginary. There's real and imaginary part associated with electronic cloud, and each of them, real and imaginary part, accumulate same phase as we go along the trajectory. And in general, we can summarize this assumption as the distribution of electrons in space with e to the power imaginary unit with action in the argument. So action is phase, and distributed electrons accepts Euler formula. Distributed likes Euler. This is, I wouldn't say last, but it is a very appropriate time to raise your hand and protest if this same offense your scientific concepts.
So you said action is the phase.
Yes.
So the more phases you have, the more action you said.
Yes. As long as you perform some motion, your action increases. If you just linear propagate, your action increases, or not your action of electron. And as action increases, the stuff that we didn't name, the stuff that oscillates, later we will call it wave function, performs oscillations that the larger the phase, the more and more oscillations it performs.
but it doesn't like to have that many oscillations. It likes to have the least number.
If it is trapped, confined electron, if it is trapped in an ion or in a molecule, then it is not allowed to move at any speed to any place. You have some limitations for motions that will have only integer numbers for action. So moving the whole cycle from one side to another, it will make integer number of oscillations or integer values for the action. So this hypothesis, so it was a big challenge for science, and before making equations, working hypothesis. When one made this hypothesis, it did allow to reproduce spectra of hydrogen atom with very, very high precision. While Bohr model was and later on, I'm just skipping this experimental stuff because it will take out 3 hours. We can return to it later. The hypothesis is accepted, and if you later summarize it in form of mathematical equations, then we can reformulate parameters of this equation for any atom or any molecule, and again get great agreement with experiment. Okay. So what we do today in our was big challenge for whole human scientific community for like 15 years, from 1910 to 1927. There were no equations, there were only ideas, hypotheses, and some arguments. And some of them sound crazy and counterintuitive. Therefore, many people hate quantum theory. Okay, so you just asked a question, but you didn't protest. Many good scientists at the beginning of the century were protesting. No. I'll skip this, but if you believe in Euler formula, you can rederive equations for multiplying sines and cosines or evaluating sines and cosines of summations of different arguments. There is a way that I will be happy to show some other things. First thing that's happy about myself in the undergraduate studies, when first you need to memorize like 20 equations and you realize that you just write 2 Euler functions for different arguments, all formulas for multiplying sines. Okay, so just relax half a minute, write your impressions or summarize. Agreed, it is agreed by now. Because we are going to not tell me that we are going to switch gears. We will be in the same direction, but we will go to more detailed goals and more, let's say, we are coming from philosophical discussions to more rigorous math. Please do not be scared. I will try my best effort to avoid mathematical derivations and boring solving problems. But at least at each step, we need to formulate problems on a mathematical language. This is unavoidable. For example, if you go to like industry, academia, you can hire experts in any area. But even if you have some, you need to formulate problems. And if you hire a mathematician, you need to formulate problem on a mathematical language. So it is an absolute minimum that we cannot avoid. So we can skip solving if possible, but we can skip formulating. So suppose everyone started to believe that something was oscillating, and this something is exponential of imaginary phase that is equal to the action. So it's distributed electronic crowds oscillate in space, and it is associated with action. No one in chemical audience would object against SPD orbitals. So suppose we have a molecule. We do have electronic orbital which is maybe superposition with SPD orbitals, but then this molecule is experiencing heating or radiation by laser or collision with other molecules. And you ask yourself, how this distribution of electronic crowds will change in time if the molecule is driven away from equilibrium. Predict future. If you know present, if you know past shape of these electronic crowds, and you want to predict how they will look like after a certain amount of time. So you want to predict future of electron, to be more specific and narrow. So the goal is to predict future. We have unspecified this distribution of electronic crowds one time, initial time, and we want to see this distribution of electronic crowds at later. This is a really good problem to pose and to formulate in mathematical language. Before we go forward, let's discuss what is the nature of these electronic clouds. What are they? How to interpret them? If you agree with SPD orbitals, what are they? If you see clouds of water vapor in the sky, you know this dense water vapor. What are the clouds of this SPD orbitals? What is inside if you touch it? Like you imagine that you touch them. What is inside? What are they? If you're not answering, it's not bad. This was also a question for like 5 years to debate in the community. It's really throw off the mind. So there are 2 interpretations, and they were like 50-50 originally. Well, maybe less than 50 and 50. Some people thought like quantum theory is garbage, I didn't believe it. But now most of people accept one and decline another, but there is a small fraction of people who, after 100 years of developing the theory, still accept the second interpretation of this stuff. So most of the common and accepted that you are invited to reproduce in public. That we develop mathematical theories for this psi function, which always need to be multiplied by itself. So absolute, you always need to take absolute value squared of this distribution. And when you take absolute value squared of this step orbital, it will give the probability distribution. It will give what is the probability to find the electron in a given vicinity of position and time. So absolute value square or wave function conjugated wave function will give the probability distribution. So if you draw these orbitals, where they are dense, there is a high probability to find out. Where they are sparse, there is 0 probability to find an electron. So electron can be anywhere, but in the denser areas, it's more likely to find. The probability. It's very hard philosophically. It means like it's still a little particle, moves everywhere randomly, and there is just probability to find it here or there. Second interpretation. that is easier to accept, but please do not say it in public. It is not accepted by today's community. That electron is like a gel. It's a distribution of charge, because electron is negative, and you can just smash it and you can just shape S and P shapes, and there is so much fraction of the charge. Like the charge of electron is -1, and in some area space there is like 1% of charge here, another percent here, and then when added together it will be -1. This is much easier to imagine, but do not say it in public. It's not commonly accepted interpretation. But right now, we speak a little bit more precisely. So we are dealing with imaginary functions, which always needs to be taken squarely, and it gives probability of finding an electron. So we are developing equations for probability distributions of electrons at past, present, and future. And we try to make this. So it is our goal. We are going more and more specified. Objections?
So how do you get that curve, the probability curve? If you multiply those to the action together and then take the absolute value, because that's what the phi is, right?
So when you multiply you will get just one. So if it is, we will get into details. If it is just exponential with only phase and nothing else, it will correspond to electron in a universe where there is nothing else. Universe consisting of one electron order. Space and electron, it moves. And then when we find probability distribution of this one electron in the universe, it will be, so we need to normalize it, it will be equally distributed everywhere. Third one. So if there is an unconfined space, it will be homogeneous probability to find it everywhere. But there are additional factors to this functional form that I'm skipping to get going. Okay?
Okay.
And this image is with this factors. Yes?
On the last slide, what is the asterisk for?
Integration. So if you have z equals x, right? And z star will be x minus 1. So swap sign in front of imaginary part. And if you draw in the complex plane, it means mirror reflection along x-axis. Changes and facing different side. So complex conjugation. Good. We can interpret the function, and now we need to predict the future. So philosophically, we did agree that as electron moves forward, it accumulates phase. And wave function gives this, obtains this factor, is multiplied by this stuff. So right now, I'm yet very far from rigorous derivations, but we approach it. So suppose we have initial distribution, and we want to see how it will change with time. So we have not homogeneously distributed, but something like localized around that. And then we let it go. And we see how the phase and the situations will develop. So there is again, hypothesis. We are only in philosophical space of hypothesis. Later on, it will be more rigorous. That if you have this distribution at t equals 0, and then we want to find this distribution at t is bigger than 0. So as far as we progress in time, there will be some motions, there will be some accumulation of phase, and the change of the wave function can be approximately taken into account as multiplication of the initial wave function by this oscillating exponentially with the action corresponding to average trajectory, how the center of this distribution of electrons is moving. So if we again, suppose we have electron localized, maybe it was hydrogen atom, electron is around the negative or positive nuclei, and then we remove positive ion so that it will be just electron cloud, and apply electric field that it moves homogeneously solid. As far as it will move forward, it will accumulate phase and start oscillating. And these oscillations can be described by multiplying original wave function by exponential with this oscillatory phase, or phase is computed for given for the trajectory that this electron is following.
Is that an S or is that an integral?
S. Time d t of x of t. So we need trajectory, and then at each point of trajectory we compute kinetic and potential energy, and we integrate it. So the dimension of action is energy times time.
I just didn't know if that was an integral from 1 to 1 or if that was S.
It was S. No objections. Yes. Understand? Okay, 4 minutes. So, goal is to go from past to the future. Now, who took differential equations? It's my favorite class. Good. So you know that differential equations can be solved analytically by pen and paper if they're simple. If they're complicated, you solve them in a computerized way. So you represent derivatives in finite differences and you propagate them step by step, right? Nature of idea. So let's represent this integral as a summation of finite differences for different intervals of time. Okay? So integral is summation of many terms at different points of time. Let's write them explicitly. So this is what I was. Oh, by the way, there is no harm if we replace L to H. The result will be the same. Each time I teach the course, I'm trying to read the literature and justify this change, but it's very bad. But it works. So if we put this accumulation of phase from initial to final time as an integral of energy, and it is something promising and beneficial. But instead of evaluating this integral as analytically by pen and paper, we can split the trajectory on each time step and represent this integral as a summation. I better write it down. So this e to the power integral dt, and we can rewrite it as e over h at time 0 dt. Times all factors, minus 9 times e minus I over e power Hamiltonian at time 1 times e to the power minus h tt, which is the same as exponential to the power minus 9 square h1 dt plus h2 dt plus h3 dt and so forth. Right? Good. So these two writings are equivalent. You can do exponential with summation in the power of exponential, or you can split the summation on the products, right? Then each of these little things will independently work as a little accumulation of phase at each portion of trajectory. So this will be evolution. It will be change of the function from time 0 to time 1. This will be evolution from time 1 to time 2, and so forth. So each time we make a little infinitesimal step forward in time, we multiply our wave function by additional factors. And these factors accumulate, they roll up together. And it gets us the propagation forward in time. So if you have wave function at 0, you multiply it by first propagation, you get propagation in time 1. Then you multiply it by second propagation, you get wave function at time 2. Make sense? Multiply again and again and get from the past to the future. So initial wave function, first propagation, second propagation, and then you finally get the prediction of the future. So we are not yet in the position to solve true problems, but we have general idea how to predict future for if we know distribution of this wave function at initial time, and we know Hamiltonian, we know trajectory, we kind of can predict what will be in the past if we practice all these things in a numerical or analytical way. Okay, I think I'm over time, and let's. Okay, I know where we stop. Let me show my favorite slide. Yes.
Is there a lab today?
No. Let's keep it for until after Labor Day.
Okay.
We'll accumulate a little more page from the problems. So, end of the lecture. Meeting is dismissed. I'll stay here if anyone wants to ask questions.
Where are you?